All right. Gearing up for Advent of Code Day 13. I know very little about this, except that someone in the Toronto JS Slack posted the words number theory, which is terrifying, because number theory is quite vast. So let's hope it's not too terrifying. Yeah, okay. And word is this one's pretty difficult. So here we go. Close the answer or the input key from yesterday, day 13. Okay. Fingers crossed. All right, shuttle search. Your ferry can make it safely to a nearby port, but it won't get much further. Oh, I should point out that as these get more difficult, tips, hints, extremely welcome. I'm not above learning new concepts. I'm not above hints. All are welcome. Anyway, let's get started. Your ferry can make it safely to a nearby port. Well, that's good. Okay, but it won't get much further. Further. See, further, I learned a little while ago, and sticks out to me whenever I read now. Further is a measure of degree, whereas farther is a measure of distance. So in theory, I think what they mean here is farther. It won't make it much farther. It won't go a farther distance. Anyway, I don't know why that always jumps out at me now, but it does. When you call to book another ship, you discover that no ships embark from that port to your vacation island. You'll need to get from the port to the nearest airport. Okay. It's giving me warnings about the stream bitrate, so I hope this is streaming. Okay. Okay, so fortunately, shuttle bus service is available to bring you from the seaport to the airport. Each bus has an ID number that also indicates how often the bus leaves the airport. Oh, that's convenient. Bus schedules are defined based on a timestamp that measures the number of minutes since some fixed reference point in the past. At timestamp 0, every bus simultaneously departed from the seaport. After that, each bus travels to the airport, then various other locations, and finally returns to the seaport. This is actually kind of funny, because in a previous life, like a long time ago, actually wrote a bus app or a bus and train app that with a trip planner. Hopefully that knowledge will come in handy here. But yeah, this is exactly how we built the schedules. Was we knew where the buses started, and we knew what the times that they started and their frequency, and we had to use those to sort of recreate the schedules. It was a bit more involved than that, but it was a lot of fun. Okay, defined based on timestamp, number of minutes. Okay, at timestamp 0, every bus simultaneously departs. Okay. And finally returns to the seaport to repeat its journey forever. Oh wow, 24-hour bus service. This is a good place. The time this loop takes a particular bus is also its ID number. The bus with ID 5 departs from the seaport at timestamps 0, 5, 10, 15, and so on, with bus ID 11 leaving on the 11s. Okay. If you are there when the bus departs, you can ride that bus to the airport. Okay. Your notes and your puzzle input consist of 2 lines. The first line is your estimate of the earliest timestamp you could depart on a bus. The first line is your estimate of the earliest timestamp you could depart on a bus. The second line lists the bus IDs that are in service according to the shuttle company. Entries that show X must be out of service, so you decide to ignore them. Okay, that's interesting. This is going to need some some further digging. To save time once you arrive, your goal is to figure out the earliest bus you can take to the airport. There will be exactly one such bus. For example, suppose you have the following notes: 9:39, and then this line of stuff. Okay. Here, the earliest timestamp you could depart is 9:39, so that's line 1. That's the time you arrive, I guess. And the bus IDs in service are 7:13, 59, 31, 19. So near timestamp 939, these bus IDs depart at the times marked D. Okay, so these leave 7 minutes apart, these leave 13 minutes apart, these leave 59 minutes apart, 31, 19. Okay, the earliest bus you could take is bus ID 59. The earliest bus you could take is bus ID 59, which is this one. It doesn't depart until timestamp 944, so you would need to wait 5 minutes. Oh, because we're at 939. I was just like, that doesn't look like the nearest bus. But yeah, I see. This is now, and then this is the bus. Okay, multiplying the bus ID by the number of minutes you'd need to wait gives 295. Okay, so we find the next departure, and we multiply that by the number, the diff in now to the departure time. Okay, what is the idea of the earliest bus you can take to the airport? Okay, cool. So this is probably not the difficult part. At least I'm hoping this isn't the difficult part, because it seems pretty straightforward. I'll bet this is just the preamble, and the really difficult part is part 2. So let's try this. All right, we've got day 13. All right, so this is going to be our test input, and okay, and then we've got this plain section, and then okay, so earliest bus you can take is ID 59, doesn't depart until timestamp 944. Okay, so we've got a couple of things that we'll need to assert here. So usual 3 sections, we're gonna have defs, tests, and the part where we run it. So what are our assertions gonna be? First, let's bring in the usual suspects, log and assert. Let's see if I can remember to require them. Require assert. Okay, so ultimately we're going to be asserting that 295 is, what is this? This is going to be the time times the, I don't know if there's a good word to describe this, the time times the number of minutes you have to wait for it. I don't know, the lull factor, sure. And that is going to be the lull factor of the bus and the wait time for that bus. So the departure, yeah, let's name these later. Okay, so we're going to assert that the next bus is 59. So we want a departure. Assert departure given parse input. We're going to assert that it's bus 59 and that it's timestamp 944 is departure parse input or next departure. So next departure, we're going to make a function that returns the bus ID and the time that it departs at. Okay, so that's roughly what we're going after. So for right now, just so we're not constantly just blowing up log or assertions every time, we're just going to do this. So we're going to need parse input, and we're going to need next departure. Okay, so parse input equals, it's going to be a wall of text, and that wall of text is actually going to be the current time equals, I guess this can just be, yeah, current time is fine, or I guess we can just call this now. Whoops, because this is when we want to leave or when we arrive. And that is going to be the first line is going to be text.split on new line. So actually, we're gonna have two lines here. We're gonna have now, and we're gonna have what's a good term, good word for this? The IDs. So this is gonna be the ID line, I guess. ID line. All right. And now we're going to parse float to get a number. And then ID line, so IDs we're gonna want, so parse input is gonna give us IDs and a time. So what we're gonna wanna do for IDs is we're gonna want to split it on on a comma. So it's gonna be ID line. I guess ID line can be schedule. Okay, dot split. And we're gonna split that on comma, and we're gonna want to filter. Here, let's split this onto lines. Filter, and I guess, you know what, we might be able to just filter on parse float, because parse float of 0 or parse float of x would be nan, and that's falsy. So let's see what this gives us, and maybe this will be good enough. So now we're going to return now and IDs. So let's see what parseint or parse input gives us. Okay, no, oh yeah, log console. Okay, so this gives us what we're after, I think. So 7, 13, 59, 31, 19. Okay. Oh, and we're gonna filter parse float. Filter parse float. Oh, and then we're gonna have to map parse float. There we go. Okay, so we've got a bus ID, or we got now, and then we've got these bus IDs as integers. Okay, cool. Next departure. So the next departure, it looks like up here, what we're gonna wanna do is we're gonna wanna just calculate the mod of the bus number and find the one that is closest to, without going under, so it's like reverse Price is Right rules. The nearest, we just want the lowest mod, I think. So if it's 939, the mod here would be 6, like 9 or 10, 5, bigger. Okay, so we'd pick 5. This is the closest bus. So next departure. So let's make next departure. So next departure, this is a function. It takes now, the time, and it takes a list of IDs. And what we're gonna do is we are going to map the IDs, and we are going to we're going to want to track, we're going to want to sort the IDs, actually, I guess. We're going to want to sort by how low the mod to now is, and then we're just going to take the first one. Now mod ID, and then we are going to take the first one. I don't know if I can do that, probably not, but also I should spell now correctly. Let's just say sorted equals, and then we'll take the sorted, the first one. And oh, next departure, what we actually want to do is we want to return the ID and the time. So so we want to divide that by that and then sealing it. So this is going to give us the ID, and then what we need to do is we need to find the departure time that it's actually going to leave at. So time departure time equals ID. So we want the one that is greater than now. So now, so we want, oops, now divided by ID, and we want to math dot ceiling that, I think. Okay, and then we'll return ID and departure time. Oops. And this should be, okay, so next departure, let's see if this works. Undefined, not number. Okay. So sort is also one of those things that happens in place in JavaScript, I think, even when you do this. So this is going to be the first ID. Let's try that. Nope, still not. So let's log IDs, see how bad it is. Okay, this is giving us 0 next departure. Oh, you know what? Because we're not exploding that. Aha, okay, cool. So this is saying, oh, that's not correct. So sorted IDs equals, maybe sort, when you give it a callback function, actually returns the sorted array. So let's take a look at that. No, it doesn't. Sort, oh, okay, this is going to give us ID1 and ID2. ID2, not sort by an ID. Unless there's sort by. Is there JavaScript sort by? Sort by. Is a function, yeah, oh, that's underscore sort by. You know what, I'll take sort by. Sure. Let's grab sort by. Oops. Sort by equals require sort by. So we'll sort by IDs and then comma. Oops. And then we're going to pass it in that. So sorted ID. So this is still not giving us. Let's log that and return. So this gives us 7 mod 9 or 939 mod 7. What is 939 mod 7? Let's find out. 939 mod 7 is 1. Okay, so but yeah, the input ID, let's log IDs. So 759, it's not changing the sort order. So that's a bit confusing because that's 7, so that's 929, 939. That's really weird. Okay, so log IDs and then sort by ID. So this is still okay. This is giving us okay. This is log IDs, which is this one, and then this is the sorted IDs. Okay, so it is actually, so something is being sorted. I think we're logging too much. I'm getting confused about what we're logging. So first of all, let's get rid of that. This is logging the output. So this is next departure that we're doing. So let's just run next departure. Okay, so this is IDs on the way in, and then the sorted IDs here. Oh, okay, this is just, so this is giving us a different answer than what I'm expecting. So 59, oh, 59 is last. So that would have theoretically the highest mod, wouldn't it? Unless you sort, let's look at sort by. Maybe we're confused about sort by, underscore sort by. All right, sort by. Sort by list iter context. Oh, we can also do min, the min value, but you can pass an iterative function. So we could actually do min as well. So maybe that's what we want to do. Let's just change tax right here. So this would be min. So this would be id equals min. So let's see if that gives us, and then let's log id. So this gives us 7 still. Okay, so $9.39. Well, let's just check these one by one. So 931 mod 7, 13, 59, 31, 19. Okay, so 1, 3, yeah. So this is actually returning the correct thing. So 59 would end up being last, and 7 would end up being first. So this is at 9:39, but this is indicating that at 9:39. Oh, look at that! This is giving us the mod. Oh, okay, so this is actually what's left over. So we're actually just looking in the wrong direction. So we want the mod plus the value. Okay, so that's interesting. So that's where we screwed up. Plus ID. Or I guess we could do ID plus. And that should give us the bus that we're looking for. Apparently it's not. So ID plus. So I think what we're looking for, so this would be, so 939, so this would give us 1, and then plus 7. So this would give us an 8-minute wait in theory. So this would be 7 times. Let's take a look at what these are. And these aren't 7, these are, okay. No, oh, these aren't multiplies, these are plus. And that would be a plus, oops, as well. So this is still giving us 8 minutes until the next bus. Oh, it'd be that minus, wouldn't it? So wait, we want, actually maybe mod's the wrong thing. Maybe what we want to do is we want to divide. We want to get a float and then the ceiling and then subtract. Yeah, okay. So let's do now divided by, and we want to math.ceiling that. So this is going to give us, yeah, plus 59. Okay, right. So that's what we want to do. We want to do the ceiling of now divided by the IDs, because that's the next bus stop that's coming. And that is also the departure time, now divided by ID. So, okay, so we've got the ID and we've got the departure time. And that's what we're theoretically returning. So we can get rid of these now. Next departure. And that gives us bus 59 departs in 16 minutes. Or this is going to give us the departure time. And what we want is we want the departure time now divided by ID. So ceiling now departure. Okay. Now it would be now times ID. No, so now let's see. Now that would give us 16 minutes. That doesn't make sense because we're at 9:39. and we want to get 944. So 944, what we want to do is we want to figure out when that's going to be. Okay, so we know the ID of the bus. We know now. So what we're going to want to do is we're going to find out we're going to find the next one, which is that, right? That is Massiel. That's going to give us now divided, oh wait, that should give us, so now divided by ID, it's going to give us like, okay, so that goes in like 26.3 times, or there's going to be 27. That's going to give us the factor that we multiply by. So ID times will give us the next departure time. At 9:44 it departs, and that's correct here. Okay. And I guess what we really want is we want to know the departure offset, not the departure time. I guess we can figure that out here, departure offset. So maybe we should pass back now as well. So now ID, so now bus ID and departure time. So that's the next departure. Okay, and then what else do we need to know? We need to know, we just need to know this. We need to figure that out, which is the difference between now and the departure time times the ID. Okay, and that's going to be the lol factor, which is our weird scoring system. Now, ID, departure time. And basically what we're going to do is we're going to, departure time, minus now times ID. Okay, so we're not really asserting that because that's going to be assuming that now is also in there, but we are going to assert this. So let's just see if this works. It does not. Oh, because we're not, it is lol factor. We're not passing anything into it. Okay. There we go. Okay, so that's correct. And we don't need to log that anymore. What else are we logging? We're logging the IDs here. Okay. Oops, we don't need to log that. Okay. So that's looks like part one. We don't need to assert that anymore. So we're going to log that for require input. And what's input going to be? Oops, input is going to be your puzzle input. Oh, damn. Okay, well, input dot coffee module dot exports equals, and let's run it and see if this is the correct answer. I'm hoping it is. That's not the right answer. Your answer is too high. Okay, so our answer is too high. Let's take a look at our input and see if there's any weird that we're doing. So this is the time, which is a lot of minutes past midnight. And then this is our bus schedule. Okay, and god damn. All right, we are getting an answer. Unfortunately, it's too big. So I guess what we can do is we can see what we're getting for log next departure. So this is giving us bus ID 829, which I'm hoping exists. It does. Okay. It's also the highest number, which is weird. So that's next departure, and then parse input. Let's just double check that parse input is giving us the same thing. So 23, 41, 829, 23, 41, 829, 13, 17, 29, 13, 17, 29, 6, 7, 7, 3, 7, 19, 6, 7, 3, 7, 19. Okay, so this is, it seems to be parsing the input correctly, and 1002632. Okay, that was a Hail Mary, but it's good to check. So next departure is giving us the wrong answer in this case. So why is that? So maybe what we can do is let's make next departures, and we'll look and see if that makes any sense. So next departures, all this is going to do is, rather than just doing it for the min, what we'll do is we'll just make a list of next departures. So we'll make ID and departure time. So IDs map ID and or ID and IDs. What we'll do is we will do ID, comma, the departure time. So next departures, let's see if next departures, first let's try it up here. Log next departures, parse input. Okay, so 7 leaves at 9:45, which does. The next one should be 13 at 9:49, 59 at 9:44, 9:61, which is off the map, and 9:50, which is off the map. Okay, so this seems to be working. So let's try what the next, let's find out what the next departures are for this guy down here. So parse input. Okay, so these are the next departures. And what is now for the input again? The now is 2632. Okay, so 2639. So this is giving us 2632, 2638, 2637, 649. That does look like the next departure to me. So that would be 5 times 677. 5 times 677 equals 3385. Wait, do I just have this lull factor? So departure time minus now. Okay. Times the ID of the bus. And the ID of the bus. So 2637. What did I put in here? Oh, I guessed a very big number. So I don't think this is, maybe I just did that wrong. What is lull factor? So next departure gives us now ID departure time. Now ID departure time. We want departure time. Let's log arguments. All right, let's just turn those off for now. Okay. Arguments is what? Yeah, let's just log these things. Okay, so we're getting now the bus and the departure time. So let's log departure time times by now. So 458 minutes in the future. Oh, okay, so let's get next departures as well. So the next departure for this is 2637, and now is 2632. So that doesn't seem right to me. Why is 458? 100 2637 2632. So that's the departure time, and this is the departure time that we're passing in. So 100 3090. So we're passing in 829 3090, but that doesn't seem right. 829 2632 26. We should be getting 677. So this is giving us the wrong bus. So let's change next departure to use next departures, and we want to. We're going to take in now and IDs, and then we're going to get back ID and departure time. So, all right. We're going to look for the min. Next departure time equals min next departures, and then now IDs, and we're going to we're going to pass in a function that takes what is it? Was it give back ID and departure time? Okay, and we are going to min by departure time minus, just departure time would be fine. And then let's return. I guess what we want is we want ID departure time. And then we're gonna return now ID departure time. So let's see if that works. So that gives us a different answer. Let's assert that this is still correct. It is. Okay, so maybe, yeah, we were just, next departure was wrong and it happened to work. Okay. All right, well, let's get rid of a bunch of these logs and see if that is what we want. Log, 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 log. So the lol factor is 3385. Okay, return to day 13. That's the right answer. Okay, cool. 3385. So that was it. We got compute our next departures. We find the next departure by finding the minimum, and then lol factor, for lack of a better word, lol factor. Yeah, that's fine. Leave the spacing like that. So we're using min from underscore. Yeah, I don't know. I'm okay with this. I really am not upset. Let's move on to day 2, because I feel like that's going to be the hard one. All right. This is, okay, part 2. Let's copy it. All right. So, for example, you still have the same list of IDs as above. So is this the input? I don't know. Let's just mark it as plain for now. Plain. Okay, in this example, so many bus IDs. Oh shit. Okay, that looks like a big number. So this is gonna be one of those optimization things, which is probably where the number theory thing came from. Okay, so let's read this. Okay. The shuttle company is running a contest. 1 gold coin for anyone who can find the earliest timestamp such that the first bus ID departs at that time and each subsequent listed bus ID departs at that subsequent minute. The first line in your input is no longer relevant. Okay, so for example, suppose you have the same list of bus IDs as above. Okay, an X in the schedule means that there are no constraints on what bus IDs must depart at that time. This means if you're looking for the earliest timestamp called T, such that bus ID 7 departs at T, so at T plus 0, okay. Bus ID 13 departs at T plus 1. There are no requirements, so is this T plus 1, 2, 3, 4? Yeah, 4 minutes, okay. Bus ID 31 departs 6 minutes and then 7 minutes. Okay, so we need a schedule such that these all line up like 1, 2, 4, 5, 7 or whatever. They all line up like that. Oh, here's the example. Okay. Wow, the only bus departures that matter are listed bus IDs, okay? For example, the list above, because bus ID is 19 must depart 7 minutes after the timestamp, bus ID 7 will always also be departing with bus ID 19 at 7 minutes after timestamp. Wait, what is that? Okay, those bus IDs can depart at other times. For example, in the list above, because bus ID 19 must depart 7 minutes after the timestamp at which bus ID 7 departs, bus ID 7 will always also be departing with bus ID 19 at 7 minutes after timestamp T. So it looks like they're giving us a hint here. They're saying the bus. Okay, so this seems like a hint as to how we should go about solving this. So in the list above, because bus ID 19 must depart 7 minutes after the timestamp, so 7 minutes after the timestamp, and this has a frequency of 7. Oh, interesting. Okay, that's a neat property. So it will always also be departing when bus ID 19 at 7 minutes after timestamp T. Okay, so that's a neat hint. In the above example, bus ID 7 departs at timestamp whatever, 7 minutes after T. This is fine. The only requirement is on that minute is that bus ID 19 departs then, and it does. So here's some other examples. The earliest timestamp that matches this list is 3417, first occurs timestamp. However, with so many bus IDs in your list, surely the actual earliest timestamp will be higher than very large number. So 1,000, million, billion, trillion, 100, quintillion? Jesus. Okay, what is the earliest timestamp such that all of the listed bus IDs depart at offsets matching their positions in the list? Okay, so probably not going to be able to brute force this. So what could we do? We could, the naive approach would be just check every 59 minutes and see if the 31 bus lines up and then move on. And if it does, then check the 19, then the 13, then the 7. We could. Yeah, I don't know. So what would that be? That would be like, so assuming we can just go every 59 minutes, that would be 31 times 19 times, where are we? 13 times 7. So it'd be 54,000 loops for the test input. And then this input is, how many numbers are these? I guess we can check in the last require parse input, require input, log Why isn't it running? Oh. Haha. So this is 1, 2, 3. So we'd want to multiply all of these except the largest together. So let's just do that and see how bad this would be. Okay. Times. So basically, I'm just trying to napkin math the number of loops this would take to produce an answer. It's probably going to be a lot. So we can skip the 829 one because we're going to be just incrementing through those because that's the largest one. So let's log that. This is the number of loops that it would take. So 1,000, millions, so trillions of loops. Okay, so we're not going to solve it this way is basically what we've discovered. Okay, we'll put that back. We'll put the assert back. Okay, so let's read all the clues again. See if we can figure out what this means. The only bus departures that matter are listed. Okay. Can depart at other times, and other bus IDs can depart at those other times. Okay. For example, in the list above, because bus ID must depart 7 minutes after the timestamp at which bus ID 7 departs. Bus ID 7 will always also be departing with bus ID 19 at 7 minutes after timestamp T. Okay, so interesting. So this is giving us a clue as to how we can collapse. We can collapse these. So bus 19 is going to be departing 7 minutes after 7. And so it will also be departing at the same time as 7. So we don't I guess in this case, we wouldn't have to worry about when bus 7 departs. I guess, so we could like just ignore bus 7 is what they're saying. So that reduces the number of calculations we have to do by 7. So that takes us back into the just trillions of calculations. In the above example, okay, this is fine. The only requirement is that in that minute is that bus ID 19 departs then, and it does. Okay, here's some other examples. The earliest timestamp that matches the list is so 17, so 13. So 13 would have to depart 2 minutes after 17. So, first occurrence. Okay, so this is giving us examples. Above example, bus ID 7 departs at this timestamp. 7 minutes after T. This is fine. The only requirement on that minute is that the bus ID 19 departs then, and it does. 788, 7 minutes after T. Oh, so they're just saying it doesn't matter. It doesn't matter if this departs then as well. It just matters that it departs 7 minutes after then. Well, we can try solving this, like, and try proving that the one way works, and then we'll see maybe if we can optimize it. If anyone's watching who knows of hints, now would be a great time. Absolutely into hints. So maybe what we could do is we could multiply, we could try to get rough alignment. Like, I think in math they call this a sieve, is like where you try to reduce the search set. So I mean, we could reduce it to every 59 minutes. So that cuts our trillions down by 60 in this case. But then how do we reduce that? I guess what we'd have to do is we have to figure out what the frequency of it overlapping is, because 59 and 31 will line up every so often. It will line up like once every, I guess, whatever 39 times 51 is, or I guess, oh, that's where you need to find out factors, right? So 31 and 59, they would line up, oh, I guess you could multiply it. They would line up every, is that right? So 9, so 10 and 11 would line up every 110. Yeah. I mean, that's one, maybe that's one way we could do it, is we could multiply all the numbers together and find out how often those line up. And then that would be, then as soon as we find, well then no, that would only tell us how often, that we'd be able to find this pattern. Maybe we have to do it incrementally. Maybe what we have to do is we have to find the first instance where 59 and 31 are the right offset, and then we can start jumping ahead by that amount. And then the next would be finding out when 19 aligns with those, and then we can start jumping ahead that amount. So we'd be narrowing in on the solution. Okay, well, that's the best idea I have so far, so let's try it. Cool. Defs, tests, and run. Okay. Cool. So let's grab some stuff from here. Okay, I've got log, assert. I'm not asserting that. Are we gonna, do we care about any of this stuff? I guess we care about parse input. That might be it. So here's parse input, and we actually only care about the schedule. But we care about the schedule in a different way. We care about the schedule and its offset. So the ID and its offset. So yeah, want ID for ID index in, so we're gonna split the text and grab the first line dot split whoops. So I mean, we're kind of, and then we want to filter parse float. So we're basically doing this. We're getting IDs. So for ID, IDX in, I guess IDs is what we want. So schedule. I mean, we already had this schedules, but or text dot split. Yeah, I don't know what I'm doing. I'm doing everything wrong here. Okay. So, okay, we're splitting that. So, and we're getting, so the ID, but we're filtering, and we don't want to necessarily filter them yet. We want to map parse float, and then for ID and index in IDs. What we want is we want to return the ID and the index. And that's what we're going to return. Okay, so this is what parse input should be, I think. So let's see if that works. Log parse input, input. Oops, do we still have input? We don't have input anymore, I don't think. Okay, but let's make input. Yeah, so this is our input right here. And we just ignore the first line. Okay. Run. Not like that matters. Okay, so this is giving us, oh right, for ID and ID is when ID. Okay, so this is giving us 7 with an offset of 0, 13 with an offset of 1, 59 with an offset of 4, 31 with an offset of 6, and 19 with an offset of 7. So it's giving us the ID and the offset. Okay, which is what we want. Okay, so now what was our plan? Our plan was to find the biggest ID, because we want to sort them. We want to sort them by the biggest, so we can take the biggest chunk out first. So let's sort them. So unsorted equals that, and then we can say sorted equals, I guess we want to just sort by the first, sort by the ID, I guess. Or yeah, do we want to by the offset? No, we want to sort by the ID. Yeah. Okay, sorted is going to be, oh, we're going to need, where is it? Underscore. So we're going to take sort by from underscore. Sort by unsorted, and we're going to sort by ID, and what was the other one? Offset. Sure, we're going to sort by ID, and that is freaking out. Undefined is not a function. Sort by acquire underscore. Where is this? On line 86. It's saying undefined is not a function. Sort by acquire underscore. Log sort by? What is sort by? Log is not a function. Oh, okay. Console.log. It's a function. What is happening here? Why is undefined not a function? Usually that means I did something wrong. Well, let's grab these and put them up here. So we got log, sort by, assert. So we've got all these things. And it's still complaining that undefined is not a function. Whoops. Okay, because that's if we're not calling anything. What if we call, let's log sort by 2, 3, lol. Okay. Let's sort by negative lol. Okay. So now it's working. Was it just because of this? Oh, okay. It's because it wasn't returning an array. Okay. Yeah, whatever. Okay. All right, so this is sorted by, right, and we want to actually reverse that. So let's just sort by the negative. Okay, so this is going to give us bus 59 first with an offset of 4, then 31, 18. Okay. Now that we have the input parsed, what we want is we want to find the first time 59 and 31 line up with those offsets. So where 55 or 59 and 31 are mod 4 and mod 6 respectively. So mod works backwards from how I was originally imagining it on the number line, whereas mod is the remainder. So it's actually, we want to go, so 59 times 31 minus, we want to get there and then work backwards to where, or I guess what we could do is we could just check every 59. So 4 plus 59 times 1, 2, 3, 4, whatever, until we find 31 mod 6. And at that point, we could move forward in groups of 59 times 31. So let's try this. Okay, so let's just try it here. So 50, so until 4 plus 59, so yeah, we could say what was it, t equals what does this actually look like? So t equals 4 times, or 59. So let's say this t equal, or let's n equals 1, or I equals 1. I is nice for this. Okay, and then until 4 plus 59 times I. Come on. Wait a second. 4 times 59. Let's just, well, true. And then we can break. So, yeah, man, I've like lost the idea in my head. That happens sometimes, it just like evaporates. So, all right, what are we going to check? Every 59 times I plus 4. So that's, so because that's the offset. So this is going to be the number that we're checking. And what we're going to do is we are going to see if that number, n mod 31 equals, so is 6. So if, then it's good. So unless it's 6, what we want to do is we want I plus equals 1. So this is going to be like the brute force approach. Sort of like, we're just kind of like roughing this in as an idea. So if that, we're going to return was it n? Return n. Or I guess what? Yeah, we want to return n. Okay. And this should be a function. This should be like lol. Okay. So let's just do that. And let's do lol. I guess we can put I equals 1 in here. Equals 1. Okay. And then we'll run lol. And, or log lol. Whoops. Log lol. Okay, so 1184. So at 1184, so in theory, we could say log 1184 mod 59 should be 4. And then mod 31 should be 6. So 4 and 6. Good. Okay, so here we've got so we got integer 1, like I1 and I2. So I1 mod 1, I2 mod 2. And we're gonna be stepping and in this case we're stepping by, I mean we're stepping by I1. So I guess what we're going to do is we're going to recursively call this function, and we're going to start it with this, and then we're going to return n, which is the first number where they match up. And maybe what we should also do is we should return the product of the two. I guess that's the other thing we should do, is we should say, okay, so we've got 1184. So 1184 mod, whoops, 59, 54 mod 59, and 11 mod 31. And this is 4 and 6, right? Okay, so 1184 times 59 times 31, or plus rather. So if we do yeah, we do plus 59 times 31 mod 31. So we should still get 4. Okay, so and the idea is the next one. Okay, so and let's just sort of verify that briefly. So lol is going to go back to no arguments, I equals 1. So the theory here is that we can narrow in on the windows. So we can make the windows, or the instances that we're checking, bigger and bigger until we get to the end, and sort of like reverse narrow in on it. So we're going to return n. So instead we're going to log n. And we'll return if I is greater than, I don't know, 50,000, and then call log, and then we'll, so theoretically what we want to do here is we want to prove that 59 times 31 and log, here let's log 59 times 31, so 1829. We want to prove that every 1829 roughly plus 1184. So 1184, and then every 1829 after that. That's what we're hoping to demonstrate. Okay, so let's just call lol. So this did 50,000 loops. So 1839, 1839, 1839. So this is showing us that roughly every 1839 these two line up. So we start by increasing by 59 every time, and then once we find the sync of where these match up, then we can start increasing by 18 whatever it is, 1839 or whatever it is. And we can do that iteratively throughout all the numbers that we have. So that's what this function is going to theoretically do, is we're going to take in the first integer, I guess, and the first mod, and then the second integer and the second mod. And what we're going to do is we're going to find what we want to find is we want to find this 18 whatever number, which is where they match up. And then when we find out where that number matches up with the next one, and so on. And we can also provide the offset, which is whatever n is. So that's what this is here. Okay, so all right, so while true, okay, so n equals I1 times I. This should be step 1, I guess, times step plus modulus 1, and we want to return n if n divided by integer 2 is m2. So then let's call lol now with the numbers we had before, which is 59, and that was mod 4, and then we had 31, and that was mod 6. Okay, let's log that, and that is freaking out. I is not defined. Step. Okay, 1184. Okay, so that is giving us n, but what we really want, we want two things. We want n, and then we want I1 times I2. Okay, oops. So this gives us the first occurrence and then the how often it repeats. And so how often it repeats, this would effectively get fed into the new thing as the number in the modulo, right? So I guess we can collapse these into a new number modulo, which is like sort of a reverse factor. So this is going to be the number, and this is going to be the mod. So now we need to find the next thing where so we're going to have num mod equals lol, and then what's the next one in the list is 19. So then we want to, let's log lol was it num mod and then 19.7. And do we still have to step in ones? I don't know if we have to step in ones anymore. I guess we could step in the minimum of the modulos. No, that doesn't make sense, because what if they're not aligned? Well, let's try that. Let's try stepping in ones and see what happens. Okay, so we get this next number, and then it's gonna num mod equals okay, and then so then that would be 13.1, and then 7.0 like that, and then log num mod. Okay, so this would give us this number 316. So let's see if that was part of what they were saying. 31. So the earliest time matches this list. Okay, departs at whatever. The above example, bus ID departs at timestamp whatever, and it does. So 106. So this is like 788. Okay, no. Oh. The earliest timestamp which this occurs. So the only bus that departures that matter are the listed bus IDs as their specific offsets from T. Those bus IDs can depart at other times. Okay. Okay, in this example, the earliest timestamp at which this occurs is 106. So just over 1 million. And these numbers are nowhere near that. So I think maybe we're barking up the wrong tree. So, right, and we want the one where, yeah, we want this one, which is always going to be an offset of 0. So in theory, what we want is this is going to be, what are we returning? We're returning that and the modulo. So we're returning, so this is giving us a number just over 3 million, and we're looking for a number just over 1 million. So what have we actually done? Have we done anything, or are we just using the wrong, thing, the wrong approach here? 31.6, and so that would be let's just start it with equals 59. Okay, yeah, so 59.4. We don't need that last step. No, we do. So maybe this approach just doesn't work, because what we're doing is we're effectively trying to find, so we're taking, oops, I don't want to, okay, so what are we doing? We're trying to take these and we're putting them here, and then we're going with bus 31 like that, and then bus 13 we're putting here. Oh, and bus 19 we're actually putting just the other side of that. Here we'll grab bus 31, bus 7, and then we'll just put them here. Oops. So this is actually how we're sorting them, and we want them to line up. So we're finding this alignment when it happens first between the first two. And then what we're doing is every so often these are going to align, and then we're trying to find the next alignment between these alignments and this number, and then we're trying to find. So I guess what we need to do is right now, and we're moving forward by 1 in each case, which is the step. And so we're basically just starting at I1 times 1, and then we're moving forward in multiples of those until step 2 is true. And then we return n, which is the number, which is the modulo. because that will be the first time that, well, I guess the first, that'll be how often it repeats. All right, hold on, bathroom break. All right. Okay, so I can delete this stuff now, so it's not just cluttering me up. So num and mod equals 59 and 4, and then we want a new num and mod that matches up with 31 mod 6. And that number, and that'll return a number in modulo. So it's the mod plus that, some increment of that number, some multiple of that number. We'll need to match up with the next one, and so on and so on. That makes sense to me, because that means that, you know, if this was mod 2, then that would line up with this. Or I guess maybe it's the opposite. Maybe this mod, yeah, this mod 2 would line up with that one. So if this was mod 2. Oh, but, oh, okay, wait a second. So bus 31, yeah. So yeah, that's basically, so if bus 31 was 2, that was mod 2, that was supposed to come 2 minutes after this one, then that would make sense. Yeah, I feel like this should work, but it's not working. So, see if anyone on the Slack is saying anything. No one's saying anything on the Slack. Okay, well, it was worth it. It was worth a try. Okay, so let's log num mod. Let's do this at every step as well. Okay, so 59 and 4, 18, 29, and 1184. So that's this offset and this repeating, and then this offset and this repeating. So in theory, so 3451. Okay, so let's log 34,751 mod 59. So that should give us 4, 31, and 19. So this should give us 4, 6, and 7, and it gives us zeros. Okay, so that's clearly where we're screwing up, I think. So 59 times 31. So maybe we're turning the wrong number. So maybe it should be that plus step. Okay, so this is taking a lot longer. 5147. So, okay, here, let's, so 42, 24, maybe it's not plus step, maybe it's plus. So number times step plus mod 1. I think I've just started a process that is killing my computer. I can hear it. Node. All right, kill, die. There you go. Please, please die. Okay. So let's think about this on a much smaller scale. So maybe did they give us a very small input? Yeah, 17, 13. So they give us here. Let's put it down here where we can see it. So they give us this. So 17, 0, 13, 2, and 19, 3. Oops. So they give us this very small example. Oops. So let's start bite size. So basically they want to know, and what was the example? 34.17. So they want to know 34.17 is going to be this. So what we would do is we would do it in this order, where we do 19 first because it's the biggest. We don't need these because CoffeeScript. Okay. So this would be schedules. So what that would mean is, so first num mod equals 19.3. Then what we would want to do is we'd want to do that with the next one, which is 17.0. And we want to do that one with the next one, which is 13.2. Oops. And then we'd want to log num mod. And then make sure we're not doing anything else down here. Okay, get rid of that. And what are we looking for? 34.17. So none of these are 34.17. So that's, maybe this is just the wrong way of going about it. Maybe we have to do it in order. Maybe we have to do, what does it say? 17, 13, 19. We could try it. 17, 13, 19. I mean, that doesn't make a lot of sense either. But whatever, we can try it. 17, 0, then 13, then 19, 3. So this should give us the same answer, 42.97. And it doesn't give a shit. Which is super weird. Is it just not done yet? Oh wow, okay, it's just freaking out. Just please die. Doing anything down there? No. Log person put input. Okay, 17. So I guess it's going on forever trying to find the third one. And it has clearly passed it. Okay, so So maybe this is the wrong way of looking at this, because they were saying 34.17 log 34.17. mod 17 should be 0. And that mod 13 should be 2. And that mod 19 should be 3. So let's see these. No, it's not. So that should be but that should be the first time when all of these things are true, right? Where 3417 should be 0, and it is. And then that mod 13 should be 2. Oh, you know what? We have the mods backwards. Should be 13 minus 2. Oh, okay. So maybe that's the problem. So when mod is M2 plus I2. Okay. So it should be 13 plus. So let's assert these. Assert 13 plus 2 is. Okay. And then assert 17 plus 0. Oh, mod 17, and this would be mod 17. I guess this would be 0 because, okay. 13 minus 2 and 17 minus 0, or 0 minus 7, yeah. Right, is mod M2. Oh, that's mod M2, we want mod I2. Okay. Okay, so, and then this one would be 19 minus 3, so 16 is assert. So that's correct. Okay, so now let's try these. And that's still going into infinity land. Okay, so we want to return that, oh, plus step. We don't care about step anymore. Okay, so 41, this is still giving us the wrong answer, which is 41.99,782. What's 41.99 minus 782? Maybe we need to log minus 3417, and that's what we want. So we want to subtract these. Okay, so num mod. So we want to do log num mod, and then we want to log num minus mod. Num minus mod. Okay. Answer. There we go. All right, so let's try that. So answer 3417, and that's what we want, I think, isn't it? 3417. Yeah. Okay. So here we are. We got our lol, and we're going to apply them in this way. And I wonder if this will take forever. Let's find out. Okay, it didn't take forever, and it gave us 106.8 something. And I think, is that what we want? 106, that is what we want. Okay, cool. So we just need a function that produces these. So this is gonna be fine. What is this, like find? What do we want? We want the offset and the mod of this. So that's going to be first common departure, I guess. What an awful name. Okay. What an awful name for a method. First, so and then we want first common departure for a set of these. So we're gonna have an array of departures, and then let's just call this one lol for now. Okay, so this is going to be an array of departures, and each departure is going to be the time and the mod, I guess for time mod in departures. And what we're going to want to do is we're going to want to continue. We're going to want to skip the first one, basically. So prove time, prove mod. So we're going to grab these equals time mod. Cool. And then we're going to continue if or unless index. So this is how we're going to skip the first one. And then what we're going to do is, I guess we're going to want to, so unless index, I guess we're going to want to do that and then continue. Otherwise, what we're going to do is we're going to have to do this at the end anyway. And then we are going to prove time, prove mod. Oh, we're not going to set that to time mod. What we're going to do is we're going to say first common departure. Prove time, prove mod, and then time mod. And that's going to give us a new previous time, previous mod. And then what we're going to do is we're going to return previous time, previous mod at the end. So that's going to be, so if we lol parse input log lol parse input, but this is going to, it's going to be an array. Undefined. Okay, so we did something wrong. So for time mod index. So we're just going to set that immediately and continue. So unless we have two different values, prove time, prove mod, time mod. And then we are going to finally return that. I guess what we could do is we could just structure it like this. We could say like, well, whatever, this probably is working. So let's log time mod. Okay, so 31, 19, 13, 7. So this is doing that, and this is logging. Oh yeah, we're logging a bunch of stuff down here, which we don't care about. That's what's fucked up. Okay, cool. Neat. So this is giving us 31, right? And what lol is doing is this is just wrapping over, and what we actually want is we want previous time minus previous mod. So this is going to give us the 106. So we want to assert that, whoops. Okay, listen. Assert 106 is hot damn. All right. Cool. So I mean, what we could do is we could just see if this works. And then we can look at refactoring it. So let's do that. Let's log lol parse input, except this is going to be require input. So that gives us this extremely large number, and we'll see if that works. That's the right answer. Holy shit, we did it. Cool. Neat. So I don't know if we used number theory really to do that, but we did certainly get creative. Okay. So let's refactor this a bit and just see what it is that we were actually just doing. Okay, so we've got our input. We absolutely need to name this better. So this would be, so first this would be find common departure, and then lol find common departure, and this says first common departure. So this is the first common departure between two sets, and this set is going to be right. I mean, we could split this into like two arrays where we have the time and the mod. So we could do time one mod one, like what was this, I1 M1. So we could do like I1 M1 and then I2 M2. This makes a bit more sense to me because it's an array of two values. It's like each one of these is grouped. So let's do that. Proof time, proof mod, and then time and mod. So is this still working? Yeah, I think it is. Okay, cool. Yeah, what was our answer? Okay, cool. Well, I don't know. Whatever. Pretty sure. Let's just go back. Yeah. Okay. So this is one thing that I'm happy about, is that, or that makes me happy, is when we can group things like this. We can group together. This is our first like group of information, which is the time and the mod that we need to match. This, while true, I'm not jazzed about, because that just opens an infinite loop that we have to explicitly return from. So what we could do is we could make this the condition. We could say until that is true. And then we would have to say like n equals 0 or something like that. And then we would return that after the fact. So does that still work? No, it doesn't. So what is it angry about? Assertion false equals true. And why is that, I wonder? N2 is N2 plus I2, N equals, so what we could do is we could do that. Okay, and that gives us the right answer. So this would be calculate n, and then until this is true, we could do it again. And I feel like that is, we could say while isn't. And then do we need this? No, we don't need that anymore. So while this isn't true, we could calculate this and then step forward. And then eventually what we want to return is we want to return the new time and whatever n was. Okay, so this could absolutely use some comments. So what are we doing? So n, and just because we're doing this, so we could say, well, n equals this, because that way we're sort of like recording what n is along the way, and that still works. So we could increment the step. Okay, so this is becoming incredibly unreadable. Okay, cool. So first common departure. So what is this actually doing? What we're saying is we want to determine whatever n is. So, and what is n? That's the next time, right? So next time is going to be a multiple of the first time. So iterate over the first time. So, and these could be given better names probably. Departure time 1, and or I guess this is, you know, this isn't really departure time 1. This is going to be like, this is going to be recurrence 1 or window size 1, window size 1, and then this is going to be M1 is going to be offset 1. Okay. And this is going to be effectively how far off of 0 that window size needs to be. And then this is going to be window size 2. Window size. Win to pow size 2. And then this is going to be offset 2. So M2, where's M2? Offset 2. Does it still work? Okay, cool. So iterate over the first time. So we want, I guess we want to check every multiple of the first departure time. And so that's going to be the window size. So it's, we should push this the other way. So offset 1 plus window size times step. So check every multiple of the first departure time and see if it lines up with the second departure time, or a second departure time. And if it does, we're going to, and if so, return the new combined departure time and window. So, and n is the departure time, and then window size 1 times window size 2 is going to be the return window size. Okay, new departure time. I guess we should say new window size and departure time. So, okay. Yeah, and this is what we have here. Okay, so that's a very complicated, it's a very complicated method. And then find common departure. This is actually, maybe what we can do is we can put that here. Okay, and find common departure is actually pretty simple. This just, given a list of departure times and window sizes. Recursively find the common ones. Or I guess iteratively find the common ones. We probably could have made this recursive as well, where we just recursively call find common departure with the first and the next until we're done. But this works, and I'm not keen on changing it. So, and then what we actually want to find is we want to find the departure time is the common time minus the window size. Minus the window size. Right. So this is like when they line up minus the size of the window, which is the mod. And then, so this is going to be time rather than mod. So priv time, priv offset. Okay, still working, still working. Okay, cool. Cool, and this is going to return sorted. We don't even need to. We don't need to do that. We can just return that directly. And what if we don't sort it? What if we just return it offset, just sorted? It still runs pretty fast. So maybe we just don't need to sort it at all. And then, yeah, okay, so that's going to be IDs. So maybe we just don't need to do that. There you go. Okay, we won't sort it at all. And I guess it doesn't matter because obviously it's still running plenty fast enough. So we don't need to do any fancy sorting. And sort by, this is the only time we used sort by, so now we can get rid of sort by. Cool, okay. So we've added some comments. Maybe we could probably stand to add a couple more. So this is just basically, let's put a thing in here, like skip the first one since we don't have anything to compare or to pair it with yet. So basically what we're just saying here, we're skipping the first one. That's all this block does. So we're going to record this as the previous time and the offset. This is it's kind of shitty. This doesn't feel great. I really not thrilled about how this method looks. Because like we've got the same thing here and we're also assigning it here, I guess. I mean, it's fine. Okay, the departure time is the common time minus the window size. And then this bit here is calculate the next common departure for this pair of times. And then the departure time is the common time minus the window size. Okay. Yeah, I don't know. I feel like maybe we could explain this a lot better, but this works and I'm okay with it. Let's see what we got here. Is there anything in here? So parse input, now IDs. We could one line this, but I don't really care to. What we could do is we could split it up into two lines like this. Whoops. Yeah. I mean, this is not the most self-descriptive code I've ever written, but it's okay. It's fine. Okay, see, still works. Yeah. Okay. Let's commit it and call. Let's put a pin in this day. Actually, you know what? We failed to go back to your advent calendar where it was day 13. We failed to put back the input as we found it, which was this stuff here in day 2. Because remember, we were like, we moved those into a particular order. Okay. Not that it matters that much, but I'm okay with that. Going back the way it was, because that way it's how the question was laid out. Okay. So that was day 13. It's been better part of 2 hours, so I guess that did take quite a while. But I'm good with that. I feel like, I don't know if what we did was really number theory. Maybe we could have done it a lot faster if we'd known the number theory. I'm curious about what that number theory is now. and it's actually something that I would like to look up. If for no other reason than because it'll probably, knowing advent of code, that concept will probably come up again, and so I should probably read up on it, just for no other reason than the next time this type of problem pops up in advent of code, I'll remember what we did this time, or what we should have done this time to solve it, and that'll give me a leg up. Okay, so gonna commit my readme. Where's getx? Add day 13. Readme. Cool. Well, for everyone who stuck around, thank you for sticking around, and yeah, I'll see you again tomorrow for another fun and exciting edition of me randomly trying